by Andrew Stewart with the title The Hybrid Monte Carlo Method on Hilbert Space.
Thank you. Is that volume okay? The talk, can you hear me? Yeah. The talk I'm going to give in some sense is most closely related to one that Jonathan Maddingley gave on Monday, in that my objective is to develop algorithms that are effective for sampling measures on a high dimensional space. So the basic objective of the talk is to discuss algorithms for sampling a measure pi given by this red formula over here. So in particular, I'll be heading towards the situation where pi has a density with respect to a Gaussian measure pi 0, and the change of measure is written as the exponential of the negative of some potential phi 0. And the basic methodology here, there's a simple take-home idea that applies to lots of these algorithms. In practice, if you sample a measure on a Hilbert space, you have to finite dimensionalize it in some way. But if you conceptualize the algorithm as being defined on Hilbert space in the infinite dimensional limit, if you can create algorithms with that property, then they will be robust under refinement of your approximation of the infinite dimensional space. So where I'm headed is to try and write down some algorithms to sample this measure, and those algorithms will be defined on a Hilbert space. The second aspect of the talk is that I'm going to be using something called hybrid Monte Carlo, and the basic idea of hybrid Monte Carlo is to use Hamiltonian mechanics to explore probability distributions. And the simple idea is to take some, in words, to take some potential for a position coordinate q and augment the state space with some momentum or velocity variables and move around in this doubled state space. And that has some advantages in terms of being able to explore the state space effectively. So I'm trying to combine two things. One, how do we construct algorithms that sample a measure on a Hilbert space? And secondly, specifically, how do we do that for hybrid Monte Carlo, which is based on a Hamiltonian mechanics formulation? And the basic problem that we have to deal with throughout the talk is that what you would think of as the natural energy, the Hamiltonian, in the Hamiltonian formulation, is almost surely infinite in the probabilistic setting that I'm going to describe. So you have this notion of conservation of energy, which drives the sampling methods, but the energy is almost surely infinite. So that's the basic idea that we have to deal with. What I'm going to do is first of all tell you a little bit about what happens in finite dimensions. So this setup here will not come into play until I get into the second section of the talk. I'll start gently in finite dimensions. I just want to tell you who the other authors are. Alex Beskos, who's at University College. Frank Pinsky, who's in Cincinnati, and Juice Sancerna, who's in Valladolid. Okay, so let me just, the first two sections, one will be finite dimensions. And continuous time. And then I'll start to work in the infinite dimensional setting in section 2, and that's where this setup and set of assumptions will apply. Again in continuous time. And then if I have time, I'll tell you about the issues that arise when you go to discrete time. Where the nature of the method that you integrate the Hamiltonian problem with are key to constructing Markov chains, which are reversible with respect to the target measure pi. And here the idea of volume preserving integration will be a key idea. Okay, so let me just start then with the finite dimensional case. and explain to you the basic idea of hybrid Monte Carlo. So that I'm just going to assume that I want to sample a measure pi, or I'll use measure and density interchangeably, which is on Rn, and that pi is given as I can always define phi to be the negative of the logarithm of pi. So I'll write phi in this way. And then I can associate with this potential phi a Hamiltonian. So I'll write the Hamiltonian this way. So it's the usual quadratic kinetic energy plus a potential energy. And the basic idea of the HMC method is that rather than sampling pi, you sample e to the minus h. So that has the disadvantage that you've doubled the size of the state space from Rn to R2n, but it has the advantage that Hamiltonian mechanics can enable one to move around phase space in an effective way. Okay, so let's M is a matrix, so M is a positive definite mass matrix in terms of mechanics. And it's a good question. So an important part of the talk, when I go to the infinite dimensional setting, will be the question of how to choose this mass matrix. It's at the moment, in this finite dimensional setting, it's a free parameter. Needs to be positive definite, but other than that, it's a free parameter. And one can choose it to optimize or improve the algorithm. And I will talk about how that's done in the infinite dimensional setting. Thank you. Okay, I will also sometimes write this in terms of the velocity variables. So I'll come to that in a moment. So the velocity variables, I will use h of p and q and h of v and q. In terms of velocity rather than momentum, I'll write the potential in this way. And so v is m inverse p, so p is a momentum and v is a velocity. And I can now write down the standard equations of Hamiltonian mechanics given this Hamiltonian. So let's write it first in terms of p and q. So I just have q dot is m inverse p, and p dot is minus the gradient of 5q. I can also write this in terms of the velocity variables. So this is just q dot is v, and m v dot is minus the gradient of the potential. Okay. The reason I'm bothering to possibly confuse you by introducing both momentum and velocity is that when we go to the infinite dimensional setting, the velocities will be well behaved, whereas the momentum, as you'll see, will not be. Okay, so where am I headed? I'm trying to show you how Hamiltonian mechanics plays a role in sampling the probability distribution pi. So just in terms of notation, let me write the semigroup for this, or group actually, for this dynamics in the following way. So I'll write the solution q of t, v of t as a mapping theta of t applied to q of 0, v of 0. So capital theta t denotes the flow of this dynamical system. Now I'm going to write down a Markov chain which will be invariant for pi and constructed through theta t. So that Markov chain is, sorry, I just need one more piece of notation. I'll let capital P applied to the pair of variables q and v just be the projection onto the position coordinate. Now I can define a Markov chain, which is defined in the following way. Qn plus 1 is projection onto the position coordinate of this flow, theta t, starting from q at Qn, and with psi, a Gaussian random variable chosen according to the distribution which is given by the exponential of the negative of this contribution to the kinetic energy. So that will of course be a Gaussian random variable, and it will be mean zero and covariance M inverse. Okay, so that's a Markov chain on Rn constructed through the flow of a Hamiltonian system on R2n. So what it corresponds to is the solution of the Hamiltonian system with randomized initial velocities. Yeah. Yeah, so it's going to be a Markov chain, so each n this will be drawn independently. So I won't write n on it, but it is a Markov chain, so it will be chosen independently at each step. Okay, then this Markov chain, so this methodology was developed by physicists and appears in a paper of Duane et al. In 1987. And the basic theorem which motivates this as a methodology for sampling the probability distribution pi is that this Markov chain, Qn, it is pi reversible. And I'll just show you quickly, if it's not clear to you already why that is, I'll just show you quickly why it is, because we want to generalize this idea to an infinite dimensional setting. Something I'm not telling you yet is to make an... why would this be useful? This would mean that if you could solve for the flow of the Hamiltonian dynamics, you could then implement this Markov chain, and assuming it was ergodic, samples from it would be representative samples from the probability distribution pi. Of course, you can't, in general, solve the Hamiltonian flow exactly, so there's an important aspect of making this an algorithm is to ask how you go about solving the Hamiltonian flow numerically and what effect that has on what I've written here. And I'll come to that later. But the key idea that I want to generalize to infinite dimensions is already here without any time discretization. Okay, so why is this? Why does this work out this way? Well, the basic fact that is exploited in this is, of course, the fact that e to the minus h as a PDF is invariant for the flow of the Hamiltonian problem. So, and most of you will have seen that before, but just in case you haven't, and to get across an important idea, how do you see that? Well, there's lots of ways to see that, but one way to see that is to write down the Liouville equation for the Hamiltonian problem. So let me write the Hamiltonian problem in canonical form. Sorry. Okay. Peter manages to only drop half of his, but I'm going to drop the whole thing. Excuse me. So that the derivative here is with respect to the z variable of h of z. So this is a compact notation for this Hamiltonian flow here. And then the Liouville equation, which propagates probability densities, given solution of ordinary differential equation with random data, is simply this hyperbolic PDE. And J here is skew symmetric. And because of that fact, this divergence can be expanded out using the divergence-free property. It can be written in this way. And you easily see that this term here is identically 0 if rho, the density, is any function of the Hamiltonian H. Okay, so this is just classical theory of Hamiltonian systems. So in particular, f equals e to the minus h will be in this category of densities which are invariant with respect to this equation. Okay, so e to the minus h is invariant for theta t, and the q marginal in other words, if you look at e to the minus h and integrate out to the v variable, it's just pi of q. Okay, so this flow preserves e to the minus h, and if we marginalize e to the minus h, we get pi of q. And the choice for psi that I've written down here, psi being a Gaussian with covariance operator M inverse, this is precisely a draw from the p marginal of e to the minus h. Okay, so by randomizing the momentum, we maintain the p marginals. The dynamics maintain e to the minus h, and the q marginal of e to the minus h is pi of q. So if you put those facts together, you deduce that the reversibility, or at least the invariance of this under pi of q. Reversibility a little bit more detail. Okay, so that's the basic idea of hybrid Monte Carlo, and it has been a very effective method of sampling a wide range of probability distributions. However, what the kind of probability distributions I'm interested in have some additional structure that would mean that what I've written down here doesn't naturally work if one considers sequences of problems where n grows. So in particular, in earlier work, and related to what Jonathan talked about on Monday, you can show that I'm going to just state this vaguely. If you look at the case where, and this is joint work with Beskos, this particular proposition, Sancerna, also Gareth Roberts and Nitesh Pillai and myself. If you look at the case where pi of q is a product, then the work involved in applying this algorithm, the number of steps required to explore this probability distribution is of order n to the quarter. In other words, it grows with n. So if you consider a setting where you have this may look like a large leap from this general infinite dimensional setting, but as you saw in Jonathan's talk on Monday, there are connections between the product situation and this more complicated setup that I'm going to go to in a moment. If you consider infinite dimensional problems that are approximated in a space of dimension n, then the amount of work one has to do in applying this algorithm grows with n. And just to normalize this with Jonathan's talk, the case for the random walk algorithm he talked about was order n. So there's an improvement in this algorithm, the hybrid Monte Carlo method over the random walk method. However, what one would like to do is get rid of n. So the aim of the talk is to make the number of steps to be O of 1, independently of the dimension. That's the goal of what I'm about to tell you about. Okay, are there any questions on anything? I'm going to stop the finite dimensional and move to the infinite setting now. Anything that anyone would like clarified about this? Sorry, thank you. These are meant to be identical, so I look at the IID case. Thanks. Any other clarifications? Okay, so I'm going to go to an infinite dimensional setting, which is on this board here, but there's a specific example on this board here. If you want to get your mind around a particular example, depends how you like to think. If you're type 1 or type 2. I'm personally, just not that you're interested, but I'm going to tell you anyway, I prefer to start with an example and then generalize, but I know that's a very bad thing to say to a pure mathematician. So depending on who you are, you can start wherever you like, but this is the setting. So I'm going to look at sampling measures pi, which are given by a density with respect to a Gaussian pi 0. And pi 0 is going to be mean zero covariance operator C. And the phi j's are the eigenfunctions of C. The lambda j's are the standard deviation. Well, the lambda j squared are the eigenvalues of the covariance operator C. And as in Jonathan's talk, these will be assumed to decay like j to the minus k. K is bigger than a half to make this trace class, so it's a nice covariance operator. And I will also use Sobolev spaces or Sobolev-like spaces, HS, which are defined through the S norm, which is found in this weighted L2 space in terms of the coefficients Qj of an expansion of the function Q in the eigenbasis given by the covariance operator. So it's useful throughout this talk to be able to switch between the function and use the L2 isometry with the coefficients in expansion of the orthonormal basis coming from the eigenfunctions of the covariance operator. Okay, so the larger S, the smaller these spaces. And just to fix things so that with this assumption on the lambda j's, Cameron-Martin space for this Gaussian measure is HK. And the Gaussian measure will charge HS with probability 1 for all S up to k minus a half. Okay? And so this will be relevant to the assumptions that I make on phi 0. So the change of measure phi 0 is going to be a function, you can view it as a function on HL, from HL into R, which has the property that it's Lipschitz from HL into H minus L. And this L must be less than k minus a half, so that the space HL is one that is charged with full measure by phi 0. There's also a bound from below on phi 0, but it's rather technical to write it down. But it's such that we can apply Fernique theorem when we can apply the Fernique theorem to get integrals against pi using this change of measure and use the Fernique theorem for pi 0. So there's some bound from below, which I can tell you about in detail later if you're interested. Okay, and what I want to do is sample that pi. So let's do an example for those of you that are like me and like an example. If we look at the diffusion bridge, so look at gradient flow plus noise in a potential V. I'm sorry, this V has got nothing to do with the velocity in the remainder of the talk. I shouldn't have called it V, but I have. So this V has got nothing to do with that V. So if we look at a bridge process where we ask that on some interval Q is pinned to be 0 at both ends of the interval, then the measure for this bridge process can be put into that setup where the Gaussian reference measure is just Brownian bridge with V equals 0, and the change of measure is given as an integral of so the change of measure of capital phi 0 is an integral over the interval, so I is 0t, of some potential phi 0, and there's an explicit formula for phi 0, but it's not relevant in the remainder of this talk. But what is more relevant is that, so the covariance operator in this case is the inverse of a second order differential operator. So C is L inverse, and L is minus the second derivative with Dirichlet boundary conditions. So this is, if you want a specific example, think of this throughout the talk, the remainder of the talk. However, the theory works quite generally, and I want to emphasize that this setup, where you have change of measure from a Gaussian, arises frequently when you apply the ideas of Bayesian statistics to determining a function, and when your prior measure is a Gaussian measure on functions. So there's a very wide range of problems that fit into this red box formulation, and this is just one, which is perhaps useful for this particular audience. But many of the applications do not have to make any reference to stochastic differential equations. Where they become probabilistic is through applying the Bayes approach to inverse problems. Okay, so what I want to do is look at this, what I've just gone through here in infinite dimensions. So I'm now going to go to this setup here, and I just want to do some informal calculation by pretending that in infinite dimensions we do have Lebesgue measure. Of course we don't, but what would we expect in this setup? If we just pretend we have Lebesgue measure, then the density pi of q should equal the exponential of minus phi 0 of q multiplied by the reference measure pi 0, which is Gaussian. So I can write this as the exponential of phi of q, and then phi of q is 1/2 q c inverse q plus phi 0 of q. So this would, if I was still finite dimensional but had this set up here, this would be the density of pi with respect to Lebesgue measure. And I'm just going to calculate as if I have such a density. Of course, the problem in general is that this is the Cameron-Martin norm, and this is almost surely infinite in the infinite dimensional setting. But let's just do this, because I can then link to the setting that we had over here. So let's look at what comes if we take this finite dimensional setting and just take phi to have this form here. So we then get minus C inverse Q minus D phi 0 Q. And likewise, we have the same thing here. So you start to see a partial differential equation coming out of this setup now. If you think of this specific example, C inverse is second order differential operator with Dirichlet boundary conditions. So this, what I've written down here, is now a partial differential equation in time, dot, and spatial derivatives coming from the fact that C inverse is a spatial differential operator in this specific example. Okay. In general, C of course will be trace class and hence compact, so C inverse is the inverse of a compact operator. May not necessarily be a differential operator, but in this specific example it is. Okay, so let's just look at what that equation looks like. And let's just, for simplicity, let's eliminate V. So we get M Q double dot is equal to minus C inverse Q minus D phi 0 Q. And just to get some understanding of what the difficulties might be, let's look at the example. But remember, to run this algorithm, what we would like to do is to choose the velocities to be Gaussian with mean 0 and covariance operator M inverse. So we'd like to make sense of this partial differential equation with this kind of data. And maybe I should have said at the beginning, this is a conference on stochastic PDEs. The link in this talk, I'm not looking at stochastic PDEs, but I am looking at PDEs with random data. So that's, I should have said that at the beginning, that's the link to the conference. So let's look at the example. And Boris asked a good question earlier, how do we choose M? Well, let's look at that in the context of this example. So this example. So what do we have? We have minus d2, what am I calling the x spatial variable? So we have this PDE here in the case of the example. And let's be specific and let's try and choose M to be the identity. So if we choose M to be the identity, then what we have here is nonlinear wave equation, semi-linear wave equation. But we have initial data, so if M is the identity, what does that mean? That means that Q dot at 0 is white noise. So to use this methodology in the case where I choose M to be the identity, I'd have to be able to make sense of wave equation, semi-linear wave equation with initial data which is white noise. And just by thinking of the case where phi 0 does not appear, you can understand that difficulties would arise from that because the white noise will propagate into the position coordinate, and this will be a nasty equation. Okay, but let me look at something slightly different, which turns out to motivate something that works well in the general case. Let's instead choose M to be C inverse. Okay, so if I choose M to be C inverse, you see I can write this equation a number of different ways, but one way would be this. So this equation, and now the initial data now, Q dot of 0, if C is M inverse, then M inverse is C. So the initial data for the velocity that we would need to implement this algorithm is a draw from the prior measure pi 0, which is the reference measure for the Q part of the problem. So it turns out this problem makes perfectly good sense. The way to make sense of it is to invert the second order differential operator and view it as an equation written. So I'll now return back to the general case, away from the example. And I'll give you another interpretation of what I've just done by choosing M to be C inverse. We have this equation, and we'd like to, of course, there's an initial condition for Q as well, which I'm not discussing, that would be, when we implement this as a Markov chain, that would be the current value of the state in the Markov chain. And psi is the random velocity, Q dot. So this equation can be made perfectly good sense of in the setting that I describe here. And I'll give a little bit more detail about that in a moment. But why is this a good equation? Well, thanks. Thank you. Why is this a good equation? Well, one way to see this is that if I take phi 0 to be 0, this is just a linear oscillator in which all frequencies are oscillating at the same rate. So in general, as a general take-home principle for algorithms, when one has a spatially distributed problems with a large number of, possibly infinite number of variables, algorithms tend to work well when everything is on the same scale. So this has the property that without phi 0, every variable is oscillating on the same scale. So that's one reason why it's good. Secondly, this equation is nice because we have a compact operator C acting on d phi 0. So d phi 0 is Lipschitz from HL to a bad space, H minus L. But the action of C on here makes this nice. And in fact, this is just, you can view this as just an ODE in HL cross HL and get existence and uniqueness in a straightforward way. And if you do that, what you find is that you get this theorem again, but now this infinite dimensional setting. So I'll call this now theorem 2. It's the same theorem, but different proof. And it's under the assumption in the infinite dimensional case that we choose the mass matrix M to be the inverse of the covariance operator. And it's for that reason that in this scaling, the momentum variables that I originally wrote down and are the natural variables for Hamiltonian mechanics are not well behaved, but the velocities are. Okay, so with this choice of M, you have this, and you also have, I should have stated this beforehand, where you have this. You have an ordinary differential equation in HL cross HL. In fact, the solution, so this solution operator is globally Lipschitz. So you can make sense of the solution operator on a space which has full measure with respect to the prior and the reference measure pi 0 and with respect to pi. And then given that, you can then show that this Markov chain is again pi reversible. However, the proof is now a little bit more complicated. And I just wanted to make a couple of comments about the proof and also to ask a question of the audience if there's anyone that knows a better way of proving this result. So we have a rather plodding way of proving it. So the proof, what's the problem with the proof? If you remember, the proof in the finite dimensional case relied on the fact, which I've now erased, that e to the minus h is an invariant measure for the Hamiltonian mechanics. So the analog of that is that we'd like to define a new measure, capital pi on Q and V, which is going to be pi 0 V, and an independent copy of pi of Q. What we'd like to show is that this is invariant, and that is in fact true. This is invariant under the flow dct. So at the informal level of just pretending you have Lebesgue densities, this thing that I've written down is just e to the minus h. But as I mentioned at the beginning, h is going to be is infinite, almost surely, in the setting where we choose initial conditions in HL cross HL. And that's because the Cameron-Martin's norm will be almost surely infinite. And h, if I were to write down what h should be, it would be v in the Cameron-Martin norm plus q in the Cameron-Martin norm plus the potential. So this will be almost surely infinite under this dynamic in this space, which is the natural space in which we want to work. Okay, so the way we prove nonetheless the invariance is in a plodding way where we simply approximate the space by finite dimensional space and then apply the finite dimensional result and pass to the limit. So a question to the general audience is whether anybody here knows any results about Liouville equations in infinite dimensions and preservation of measures given by density with respect to Gaussian by Liouville, through a Liouville kind of argument or something more abstract. There is, as many people here know much better than I do, a notion of Kolmogorov equation in infinite dimensions. So what might make a slicker proof of this would be some way of making sense of Liouville equation in infinite dimensions.
Just to clarify, in your H, the only two terms that are difficult are the first two.
These two are the difficult, yeah. So those are almost surely infinite, this isn't. Yeah. So the method of proof is to finite dimensionalize, so we project on.
Why are you resisting working against the natural Gaussian measure given by the first two?
I mean, that's of course what you want, but the question is how do you do the proof? The proof I showed you in finite dimensions is based on roughly on the Liouville equation and the fact that you preserve e to the minus h. So how do you prove that in infinite dimensions when h makes no sense? Of course, we are working relative to the natural Gaussian measure. So this setting means that, so pi 0 at pi, sorry, to answer your question, this is capital Pi now for Q and V, is again e to the minus pi 0 of Q, where pi 0 is just so the setting you describe is the right one, but our method of proof is to finite dimensionalize, use the proof in finite dimensions, and then pass to the limit. Of course, everything that's infinite dimensional at some level is doing just that, but my question to you is whether there's some abstract theorem that I should be using about conservation of measures given by density with respect to a Gaussian by deterministic flows. If anyone knows anything about that, I would be grateful to know.
Is there a notion of pi reversibility you could use, like similar what we're doing in infinite dimension?
I mean, that's
just check detailed balance. Right?
Yeah. So that's the same thing would apply to that.
Okay.
It's all the same question. How do you make sense of these things in this setting where you have density with respect to Gaussian? Do I have 5 minutes? Okay, so I just finished by telling you about what I haven't told you about is time discretization. And I'll tell you what happens in the finite dimensional setting, and I'll tell you why it goes wrong. So the operator splitting methods are used because the key thing that one needs, I won't have time to write this down, but you approximate this by a numerical method, and then you have to accept or reject to make it reversible with respect to pi. And the key thing that drives this is using a volume preserving integrator for theta t. So in the finite dimensional setting, the way one would do that is doing the following split, which I'll write down. So you would look at the equations given as follows. So this is what Duane et al. Did. And this, what I'm about to describe, corresponds to those of you that know about geometric integration. This will correspond to the Verlet method. I'll just write down a bit of notation. So I call this the flow of this problem theta 2t, and the flow of this theta 1t. And then the idea of the Verlet method. So this is a good way to construct integrators because both theta 1 and theta 2 can both be solved exactly, and because they are themselves Hamiltonian, they're volume preserving. So you can compose them and create volume preserving integrators, and you can compose them in a way which gives rise to what are known as reversible volume preserving integrators, although that's a different reversibility from Markov chain. So the key idea is that one works with one step of the integration, just given by the composition of these in the following symmetric way. Okay, and if you do this, now you integrate with this, apply this over t over h steps up to time, or t over h steps. And then in addition to the Markov chain, one has an accept reject, which I don't have time to describe, but it depends on the change of the energy over the numerical integration. So in the exact integration, the Markov chain that I wrote down at the beginning preserves the energy. It turns out if you use a volume preserving reversible integrator, your accept reject criteria that would preserve detail balance depends only on the change in the energy. So the problem is, again, in the infinite dimensional setting, this delta H is almost surely infinite, because H is almost surely infinite. And so you can't apply this method as I've described it. However, by a small tweak of this algorithm, you can easily ensure that it does. And that tweak is to take this linear part and put it in theta 2 and remove it from theta 1. Now, a point about this is that theta 2 preserves exactly the Gaussian reference measure. And this is somehow a trick that applies much more generally than this problem. When you're dealing with measures given by density with respect to Gaussian and you want to construct algorithms, if you build in your knowledge of preservation of Gaussians, you can do a lot better in constructing the algorithms. So this particular splitting preserves the Gaussian, and as a consequence, with this particular splitting, delta H is almost surely finite, and you can implement an accept reject criterion and get an algorithm which looks like the one in the box at the top board, with theta t replaced by this numerical integrator composed with itself up to time t, so t over h steps, plus an accept reject. And that then gives you an algorithm which is defined on the Hilbert space and is reversible with respect to this pi. And then has the property that if you run it, the number of steps that you require does not depend on the dimension of your finite dimensional approximation of the infinite dimensional space.
Your meta theorem about building the split step integrator that preserves the Gaussian measure in the underlying column, when you said better, what did you have in mind? I mean, do you mean stability properties? Do you mean this type of
What did I say was better?
You said it was better.
It's better because it's exact. It preserves the Gaussian. So if I were to look at phi 0 to be 0, this algorithm would be exact and it would never reject. So it gets the Gaussian part of the measure correct exactly. Any other algorithm, like the Verlet method, will make proposals which lose absolute continuity and kick you into some other space.
Other than the finite dimensional approximations on the way to the limiting measure, I'll always be on the right.
Always on the right.
I'll be charging the right parameter.
Yes,
I'll be charging the right space.
Yeah. So there's some theorem that says exactly that. So this algorithm will generate things which remain absolutely continuous with respect to the right Gaussian, and that somehow is the idea about how to make good algorithms, and that's of course what we're controlling in your random walk talk, where that doesn't happen. Okay, thank you.
Question?
Well, I've succeeded in doing something. I think it's the first talk I've seen with no questions at the end. That's impressive.
Thank you.